certainly looking forward to a future where I could come to Poland in person and where we can all travel again and see each other in person again. Yeah, I think if I were talking about Let's Encrypt, it would be less controversial material, because Let's Encrypt generally is something that has pretty broad, wide support, broad appreciation. This project is an internet standards project that's raised a fair amount of controversy. And I'm not sure that everyone will be as enthusiastic about it, but I'm looking forward to sharing it with all of you. So I'm working with John Gilmore on a project called IPv4 Unicast Extensions. And this project is an internet standards project and engineering project to attempt to unreserve a very large number of IPv4 addresses that have gone to waste, that are not being used. In particular, we're proposing that 4 kinds of IPv4 addresses that have been reserved for future use or for specific protocol functions should be unreserved. And we're asking implementers, like operating system developers, to treat these as ordinary unicast addresses. And that will potentially create a large amount of free IPv4 space that could be put to use meeting some of the demand for v4 space. We'd also like to test the extent to which these addresses can usefully be used on the internet, to see how well this would work, to see how broad the compatibility would be, and the extent to which ISPs are able to route and accept announcements for historically reserved addresses. If that works, then probably some years from now, these addresses can be allocated in some way. So a lot of the addresses that we're looking at are ones that were given special meaning or special status during the 1980s, decades ago, when it was less clear that the internet would become a global network. It was less clear that there would be such demand for IP addresses, and it was less clear that scarcity would be an issue. And so at that time, it was plausible to say, oh, we're going to reserve a /8 for a particular protocol function. We're going to allocate /8s to individual organizations. And now that the internet has attained the global status and importance that it has, and looking back on this, we might say, wow, you allocated the /8 for that? You allocated such an enormous amount of address space for that? And that's address space that could be used more efficiently, could have been used more efficiently, which wouldn't have been clear at the time, wouldn't have been as evident. I think most people watching this presentation will know that there are different dates that have been assigned to when the internet ran out of IPv4 address space. The IPv4 address space using only a 32-bit address has a mathematically possible maximum of 2 to the 32, or about 4.2 billion addresses, which is conspicuously lower than the population of the world. And of course, there's a lot of overhead of various kinds. That means that not all of the address space that's allocated can be used. So the most obvious definition of running out of address space would be the moment at which the RIRs could no longer make new allocations of previously unallocated addresses to operators. And this occurred about a decade ago. And address space from that time really became a significant economic resource. And there emerged fairly significant secondary markets for reallocation and transfer of historic addresses, often for millions of dollars. So fairly significant amounts of money. And we've been concerned that, especially in the cloud hosting space, there's a lot of demand on the part of operators of public services for v4 addresses, because people still want to interoperate with the v4 network and with clients that may be v4 only. even sites that are extremely enthusiastic about v6 and operators and service operators who are extremely enthusiastic about v6 still commonly find that they have a lot of users who are v4 only, and so they need some v4 address resources for their own public services. So despite this huge pressure, really substantial amounts of the IPv4 space remain unallocated or unused. And there's an interesting conversation, which is not the subject of this talk, about legacy allocations and the possibility of persuading recipients of legacy allocations to return them or to resell them. And there are numerous interesting stories about that. And the US government, for example, has enormous amounts of possibly unused IPv4 address resources. And it's interesting for people to dig into some of those and try to find out if they're really being used, if they could be returned or not. The focus of our project is not legacy allocations, but rather reserved and special purpose address space. And so we've prepared 4 internet drafts at IETF that propose to unreserve different kinds and categories of historically reserved addresses for unicast use. When we say unicast use, that means making them possible to use to number individual hosts on the internet. So this contrasts, for example, with multicast or anycast, according to some people. So we've got these 4 categories. We presented the first 2 of them at IETF 112. We're hoping to present the other 2 at the upcoming IETF 113. We also have another draft about the relationship of IETF to IPv4, which I'll talk about later on in this presentation. And I'm going to briefly talk about what each of these kinds of addresses are, how many there are, and what it would mean to unreserve them. And just to be clear, unreserving them does not mean allocating them. And I'll talk about that later on as well. So we're currently focused much more on operating system behavior. That is, attempting to get operating systems and devices to accept these addresses as valid. That is different from saying that a particular organization has the right to use them on the public internet, which is a later question. And perhaps a more difficult question, but in any case, a question that is likely to be several years down the road. So the first category of addresses is the lowest address in every subnet. So suppose that we have a /24 network. In the 1980s, Berkeley, authors of a very famous TCP implementation. In fact, the fame of that implementation was one of the things that drew me here to California. I really was excited by California for many reasons, but one was, wow, Berkeley is here. They made the original BSD implementation, and it's so famous in computer science. And I did even choose to attend university there, partly based on the fame of Berkeley in computer science and computer networking. And I did study computer science there, although I didn't finish my degree. But that was a very influential thing. And one of the ways that it was unexpectedly influential is that they made a choice of the segment broadcast address using the lowest address, or the .0, from the point of view of a /24 network, while other developers elsewhere chose the highest address, or the .255, from the point of view of a /24 for the broadcast address. Now, there was no standard at the time. And so neither of these was right or wrong, but they were different choices. And later, the highest address won in all internet standards, in all documentation, but the lowest address was continued to be a reserved address, explicitly for backwards compatibility with systems like 4.2 BSD, which have not existed on the internet for decades. And so this is a very diffuse, very widespread waste. It's also a very small amount of waste for any individual organization or network. It's one address per subnet across the entire internet. An interesting thing about this change is that even under existing standards, it's something that can be fixed locally. It's something that can be fixed on an individual network, because hosts outside of your network are already not permitted to assume your netmask because they don't know where subnet boundaries occur in networks that are not local to them. That means that if your router and your local network support the lowest address as an unreserved unicast address, existing standards imply that the rest of the internet should already be able to interoperate with it. And you can find examples, and I'm not allowed to assume the subnets of these. You can find examples from Amazon's test page that end in .0. So if they were /24 or smaller, then that would be the historic lowest broadcast address. And you can see that these are already reachable and usable under existing standards. And again, we don't know if they're the lowest address or not. We don't know what Amazon is doing. We don't know if they've applied patches like the ones that we've created, or what their subnet masks are or are not. But this is just a demonstration that addresses that may well be the lowest on a subnet can actually already be used as long as the software at the end supports that. Now, the largest category of addresses, and the one that many people will have heard of, is the former class E, the so-called experimental block. And that's all of the IPv4 addresses from 240.0.0.0 on up. And a decision in 1983 designated these as reserved for future use. So we think that, at least relative to 1983, it is the future, and it is already time that these addresses ought to be used. At that time, there were lots of reasons to suppose that new addressing modes might be created. And in fact, multicast had not even been specified at that time. And so there was thinking about new addressing modes like multicast addressing. There's an RFC that indicated that perhaps anycast addresses should have their own address block and should be treated specially by routers, which is not the way that we do anycast today, but that was a perfectly plausible proposal. There were proposals, and there have been repeated proposals, to have an address space dedicated to escaping to a larger address length as an alternative to native IPv6 on the wire, which would be sort of like an equivalent of UTF-8 in character set encodings, in the sense that we can have greater than 8-bit character sets and have some of the character address space indicating this is a multi-byte character. In any case, none of these proposals have actually come to pass. None of them have actually been deployed. And it's very unlikely at this point that new IPv4 addressing modes will be invented, which means that the original, very plausible rationale for having such an enormous number of reserved addresses is no longer really applicable. Now, there also happens to be a /8 right at the very beginning of the address space, 0/8, or the zero network. This is reserved, again, for historical reasons, due to a decision in 1981 about an ICMP-based auto-configuration mechanism that hosts could use when connecting to the network initially. The auto-configuration technique that we use today is typically DHCP, which uses only one of these addresses, not 2 to the 24. And the ICMP-based mechanism that would have used the zero network this way was officially deprecated back in 1989. Unfortunately, the deprecation in 1989 left all of these addresses still reserved for this deprecated auto-configuration protocol. And so they're still not being used for anything productive. Probably the most controversial thing that we've focused on is the loopback network, 127/8. The entire /8 was designated for loopback by a decision in 1986, with all of those addresses meaning this system. Now, in contrast, IPv6 has only one loopback address, the :1, instead of 2 to the 24 loopback addresses like IPv4 has. There are interesting discussions about useful things that you might be able to do with such a large number of loopback addresses, but we have not found applications that are using them in the wild. There does seem to be a VPN product in Japan that uses them as unofficial private address space. And the developers of that are unhappy with the idea of redesignating this. So far, that's the only application that we're aware of. And certainly if people are aware of others, it would be great if they could let us know. We would certainly like to know about obstacles and difficulties and complications of our proposals. But our proposal is that we can reduce the loopback address space to 127/16. So all addresses beginning with 127.0 would continue to be treated as loopback, while other addresses would be treated as unicast. And that is the most controversial of our 4 proposals, and it got a lot of attention. I don't know how widely debated it was in Poland, but over in the US, I heard a lot of people debating it, and even a friend from high school contacted me and said, "Hey, people at my work are arguing about this proposal. Is this yours?" It is indeed our proposal. And I'm not going to talk about multicast, but I have a slide mentioning that the former class D, or multicast, is reserved in a different way, and the great majority of those have never been allocated, although there certainly are multicast services on the internet. But we don't have a draft related to that address space. Okay, so the number of addresses that we're talking about would be 1 address per subnet across the entire internet for the lowest address. And of course, since we don't know how many subnets there are, we don't know how many addresses that is. For the 240/4, it would be more than 268 million addresses, or more than 6% of all of IPv4. And then each individual /8 represents about 1/3% of all of IPv4. So in total, we're talking about hundreds of millions of IPv4 addresses. Now, some people are surprised to learn that there is pretty widespread existing software support for many of these addresses, in some cases due to our project submitting patches. But for 240/4, there was a prior proposal in 2008 that this address space should be unreserved. And at that time, although that proposal did not pass consensus at IETF, a lot of operating system implementers thought it was a good idea and acted on it. And so the result is that quietly, most operating systems adopted support for 240/4 decades ago, more than a decade ago. And that includes Linux, everything based on Linux, like Android, and it includes Apple's operating systems and several others. The lowest address, we've created patches for which have been merged in Linux, and we, with support of Mike Carroll's from FreeBSD, have also gotten a patch in FreeBSD. And our project has also gotten a patch in Linux for 0/8. And we're not aware of any operating system that has implemented the change we propose for 127. And we have created a patch for Linux, but not proposed it for deployment by default. So creating these patches is pretty straightforward. It mostly consists of removing special cases in operating system kernels and then testing to make sure that that works. One thing that's very interesting about these changes is that typically no one notices when they're made. And so we're continuing to work on these and propose these. So I mentioned that typically no one has noticed. And indeed, a lot of the changes that we propose have already become part of existing operating systems. And to our knowledge, nothing bad has happened as a result. They haven't caused any problems. Now, we again were not the ones who made the 240/4 change, although we advocate it from a standardization point of view. That was made by other people, It was made in Linux in 2009. It was made in other operating systems in a similar time frame. And so it's quite possible that you're watching this presentation right now on a device that's capable of using 240/4 as unicast. Now, we've attempted a number of times to test that by using 240/4 addresses as private address space. And so we've made Wi-Fi networks that will allocate addresses from 240/4 and then NAT them. Typically, clients other than Windows have worked fine out of the box with no special configuration and no problems. You can try that easily for yourself, configuring a Wi-Fi router or something to allocate addresses from 240/4 instead of the RFC 1918 spaces. If you have trouble with your router, feel free to get in touch with us. We've learned something about that. We'd like to learn more about it. I like to call these MarsNet when we create such a network, as a joke on the notion of Martian addresses. And as I mentioned, most operating systems do seem to support this. Microsoft is really the outlier in the large operating system vendors in actively forbidding interoperability with these addresses. And so Microsoft has said, RFCs say that these addresses must not be used, and that's the behavior of their operating systems, that they'll actively reject packets and actively refuse to generate packets involving 240/4 addresses. Other operating systems are generally okay with it. So we think that making a change like this will have to be a gradual process. Of course, if two machines disagree about whether an address is valid or invalid, and one of them tries to use it, the machines may not be able to communicate. And it does take time to update software. And with the exception of the lowest address change, with the exception of the broadcast change, we need the change to be made on both sides. And so it will certainly take some time to get widespread support for these changes. Now, it really seems like an unfortunate missed opportunity that the Fuller, Lear, and Meyer draft, which would have unreserved 240/4 in 2008, wasn't adopted. If it had been adopted, we would have had an enormous amount of time to get these changes into the field. Probably Microsoft, probably major router vendors would have acted on that promptly, and we would have had many years of deployment to get these changes rolled out. Since that didn't happen, the next best time to start would be now. And there's a famous saying that the best time to plant a tree was 30 years ago. The second best time to plant a tree is right now. And so I'm thinking of some of these changes as akin to planting a tree. It would have been better if the changes had been made in the 1980s. It would have been better if the changes had been made in the 1990s. It would have been better if the changes had been made in the 2000s. Since these changes have not all been made, it would be good if the changes were made now, so that we're not back here a decade from now or 2 decades from now saying, oh, I wish we had unreserved 240/4 back in 2021 and 2022 when we had the opportunity. We would certainly like to work with the internet measurement community in order to see how well this would work. There are various ways that that could be done, and we're thinking about that and talking about that. And we'd like to get empirical data and run empirical studies about compatibility and routability of reserved addresses. An analogy that I like, that perhaps not everyone will like, but you can see how it strikes you. In 2018, Cloudflare got permission to use the very low and very memorable address 1.1.1.1 for a public DNS server, a public recursive resolver. Now, a very large number of networks had actually hard-coded blocking that range. And Cloudflare undertook a major effort to look into reports of people who could not reach the 1.1.1.1. And they worked with internet service providers to remove blocks and to remove problems with reachability. And that worked very well. And this address is extremely widely reachable now. It's presumably still not completely reachable everywhere because there are presumably firewall rules still hidden here and there that make that service unreachable, but the reachability is very good. And we believe that we can follow a very similar process where the formerly reserved addresses will start out with comparatively low reachability. And if there is a widespread consensus and there is widespread software support, we can look at where the obstacles are and get reports of where the reachability problems are and then address them. And this process is often called debogonization because addresses that are invalid are often referred to as bogons because they're bogus. And so if you reverse that process, it can be called debogonization. So we've heard quite a bit about people's concerns about these ideas, both when we presented them at IETF and in participating in networking mailing lists. Most of the concerns were about the 127 proposal, but some of them were broader and some of them applied to the proposals in general. And I do want to point out that the concerns that one might have about one of the proposals may be different from the concerns that apply to another one. So for example, if people are concerned about compatibility, they might still want to support the lowest address proposal because you can use that pursuant to existing standards by patching your own network. You don't need anyone else to make any change in order to use the lowest address. Of course, you only get one IP address per subnet, but on the other hand, you get one IP address per subnet. And the concerns that people have raised include both technical concerns and policy concerns, which is to say some of the concerns are about whether these ideas would work, and others are concerns about, is this a good idea? Is this something that we ought to do? And so I don't want to attempt to rebut or respond to or react to every concern that I've heard or every objection that I've heard, but I'm going to just mention a few of them. And if people have interest in this, you can certainly contact us by email. We're happy to discuss it by email. You can certainly ask me questions after the end of the presentation. So I think the largest category of technical concerns is about compatibility. And this is based on the observation that not all systems will be compatible at first, that it may take many years before all systems are made compatible, and that indeed that's something that may never fully occur because it can be hard to upgrade systems on the internet, and it can be hard to make an internet-wide software change. And I've noticed that, we mentioned that I worked on the Let's Encrypt Certificate Authority project. Let's Encrypt had an interesting backwards compatibility problem last autumn when the certificate from IdenTrust that had granted trust to Let's Encrypt services, the so-called DST-X3 root certificate, expired. And root certificates do expire. The X509 requires that certificates have an expiration date. And when they expire, it's really kind of a problem because clients may no longer accept signatures that chain up to a particular root. And there are a lot of clients out there, and some of them can be tricky to update. Some of them may be operating systems that are no longer receiving vendor updates, operating systems that have never received vendor updates, operating systems that their owners don't know how to patch or aren't interested in patching. A big source of this right now on the internet is older Android phones, which may be out of support from their vendors, but still used by their owners. So I mention all of that by way of mentioning that I've seen how it can be really tricky to update everything on the internet or to update everything on the internet quickly. And when we have backwards compatibility problems, which are not only caused by new standardization work, but also by events like certificate expiration, it can be a lot of work. And so some people are concerned about that. And they're concerned also that it may be an easy matter to land software changes in an operating system kernel, especially open source operating systems. The patches required are quite small, but operationally, debogonization may take a long time and may take a fair amount of work. And so that's one category of things that have concerned people. Some people also worry that maybe there's some kind of harm that might result if we change the meaning, if we change the semantics of some kind of internet address. And so people have worried that maybe it will cause some kind of security problem, some kind of reliability problem. One analogy that people might make is that there was a security vulnerability in some Linux systems that used a Linux kernel feature called route local net. This is a long story. I love talking about route local net. It's kind of an obscure issue. And it might be the kind of thing that makes people worry that if system A and system B disagree about what a particular address or kind of address means, that maybe something bad will happen. And in the route local net case, there was disagreement within a single system about the meaning of addresses in 127 loopback range, where some of the software on the system treated it as host scope, and some of it treated it as LAN scope. And that disagreement led to security problems. Now, I have thought about this a fair amount, and our patches don't create this problem because they completely change the scope from host scope to network scope. But having said that, people may imagine that there may be security problems when machines disagree about the meaning of something, because quite a lot of security problems that we encounter on the internet have to do with two different pieces of software that interpret something in different ways that ought to have interpreted them in the same way. And so that's an interesting area for discussion. We have not identified, and we're not aware of anyone else having identified, any specific security problem that results from our proposals, but we're always interested in hearing people's ideas and concerns. Now, the biggest objection that we've heard, for example, at IETF, is from people saying, why not just use IPv6? One of the motivations for the invention of IPv6 was mitigation of address scarcity. People realizing that IPv4 was likely to run out and wanting a much larger address space, wanting the 128-bit address instead of a 32-bit address size. So we think that IPv6 is simply not a direct substitute for IPv4, and IPv6 address resources are simply not a direct substitute for IPv4 address resources, at least from the point of view of any individual internet adopter or user. And we can see this, as I mentioned earlier, with websites that may be run by people who are extraordinarily supportive of IPv6, who think v6 is very important and very worthwhile, and still commonly, with a few interesting exceptions, but very commonly, really overwhelmingly, want v4 addresses for their public services. And people experience a lot of pain about this because they want to be able to interoperate with the rest of the IPv4 internet. And to some extent, this is a problem that is more acute or more intense for cloud hosting services compared to, for example, residential access networks. Because the residential access networks may find that many of their users are willing to accept solutions like CGNAT, carrier grade NAT, in which the internet service provider performs NAT on behalf of all of its customers. And so if customers are willing to accept that for their access networks, then IPv4 scarcity for the access provider is much less of an intense problem, because many people can share a smaller number of IPv4 addresses, or NAT can even be performed from v4 into v6. And so conceivably, some operators may not need any public v4 addresses if their customers are willing to accept CGNAT. But the same solution doesn't work as well for hosting of public services, because there, if you anticipate people connecting in v4, you're going to need v4 addresses for them to connect to. And the ability for servers to share v4 addresses does exist to some extent for some applications, but less so. And there are more technical limitations and more operational limitations. Now, as a further point on this concern, some people say, well, why would you even work on v4? Because we need that work to go into v6 adoption. We need that work to go into v6 support. So we think that this really, for most purposes, is a false dilemma, especially for the phase of our proposal that we're advocating right now, which is in terms of operating system and software support. For people working on operating systems and working on network stacks in operating systems, almost all operating systems already have complete and excellent v6 support. They're not delaying their v6 support, but rather it's an operational problem. For example, the device that I'm giving this presentation on supports IPv6 perfectly. And I have, in fact, used IPv6 many times on this device with this operating system. But my residential ISP does not offer v6, which I think is very unfortunate. And so the obstacle to me, for example, in using v6 here in my current setting is not about software support. It's about my ISP not offering v6, which I wish they would. So I don't think that this is the specific dilemma or specific obstacle facing v6. I don't think that if people somehow don't support our changes and don't support our proposals, then v6 adoption will somehow happen more, or happen sooner or faster or better. Some people have taken this objection further and said that in their opinion, no one ought to maintain or improve IPv4 anymore. We think that's a real mistake. v4 is the most used network layer protocol in the world, still carries most of the traffic on the internet. There's still quite a bit that may need to be done with it and fixed in it. There was an attempt to find consensus at IETF to completely stop work on IPv4. There was a working group called Sunset 4. It ran for about 7 years, and it proposed the deprecation of v4 or forbidding IETF from doing maintenance work on v4. The existing IETF policy requires v6 compatibility, which I think is completely appropriate and completely correct. It does not require neglect or abandoning v4. So we might say that IETF policy, as far as it's been formalized or articulated, supports a continued dual stack approach and dual stack work and dual stack services. And people may envision a far future in which v4 is no longer used or widely used on the public internet. Perhaps it will still be used even then on local networks, on LANs. But we don't need to predict exactly when that would occur or exactly what that future looks like in order to appreciate that there is significant use of v4 and significant demand for v4 and significant work to be done on v4. And so to articulate that, we have proposed another draft. It was actually created just 2 days ago, uploaded to the data tracker. And we're also proposing this for IETF 113. And this is an internet draft proposing the opposite consensus, one might say, compared to the Sunset 4. This draft says that IETF will continue to maintain IPv4 in the interest of its user community, while maintaining and not changing IETF's policy to promote adoption and implementation of IPv6. So we're looking forward to the discussion very soon of this higher level policy issue of the appropriateness of continuing to work on v4 and continuing to fix IPv4. So we've seen that v4 addresses have really significant economic value. Hundreds of millions of dollars have been paid for large blocks. And one concern is that v4 addresses are becoming a noticeable component of the price of hosting in many places, in many cases. So if you want to have a website, one of the big things that you're paying for is v4 space. Now, I've met people who are actually happy about that, and they say it's great that hosting a website is becoming more expensive because of v4. This is going to make everyone want to use v6 only. And I don't think that's true, and particularly I don't think that's true because I don't think that someone who wants to have a website somehow has the power to get everyone, like my ISP, to switch to v6 only, or to even switch to being v6 capable, right? So if I wanted to put up a website for my business, which I did, or if I wanted to put up a website about some cause or some idea or some service or anything, there's nothing that I can do as a website operator to mandate and require that everyone else in the world be able to reach my website in v6. And I may believe, and I do believe, that it would be a good thing if they could, and it would be desirable if they could. But there's nothing that I can do unilaterally to mandate or require that. And so making it more expensive for me to get v4 resources doesn't seem to actually do anything to make v6 come sooner or be more used or happen sooner. So we will have this discussion, I think, at IETF 113, just a few weeks from now. But I maintain that neglecting v4 is not a transition strategy for v6 adoption. That the problems of v6 adoption come from other factors and not a problem of v4 being too good or too reliable or too inexpensive or too anything. So we have been making software changes in various operating systems. We've been testing their behavior. We would like to do this test on a wider and broader scale and a more representative scale. We'd like to work with the measurement community. We do think it will be years before the addresses can be allocated like other unicast addresses. It's possible that that will never occur, and they might, in that case, be used in some other way. For example, as private addresses. That is something that a number of internet companies have already been doing unofficially. For example, we've heard from several companies that are using portions of 240/4 internally as unofficial private address space, which is still something useful. In our opinion, it's not as useful as the ideal of having the addresses be allocated for global use, but it's still useful to have more private address space that works. And we think that even years from now, there will still be a demand and these addresses will still be useful. And so it's okay if it takes time to make these changes. It's okay if it takes time to test these changes. The changes will probably still be useful afterward. So there are various things you can do if you're interested in this. You can, of course, get in touch with us and talk about it. If you know about things that work with historically reserved addresses or things that don't, or problems that would be caused by changing their status, you can let us know. We want our drafts to be informed by the experience of the community. You can try out reserved addresses on your own networks and see which devices do or don't accept them. We would love to have more support for our proposals at IETF. We would love to have more vendors supporting these address ranges. They typically just have to remove special cases from their software. Very small changes. If you're not already running internet measurement nodes like RIPE Atlas or NDT server or ARC on your network, it's a great public service, not just for us, but for everyone, to host these nodes that people can use to run experiments, to run connectivity tests. We don't have commitments from these projects, but we may be able to run experiments related to reserved address space in the future with one or more of these platforms. And so just having widespread support for measurement tools may become helpful to us. And keep an eye out for discussions about future testing that we may do or propose or seek help with. So that's all I've got there. It looks like we have about 10 minutes left for questions or comments. And I think we can go back to the studio now.